For problem number 3, it's a buffer problem, but it's a buffer problem with a twist because it has given you KB of the system rather than KA, but it's no problem because it's a buffer. Both are present. And again, you can't do this trick if you're just talking about what's the pH of a weak base, but if you're talking about a buffer system, then both the acid and the base are present, and so consequently, you can take the base Kb that you are given in the problem and move it to a Ka system instead, because again, it quite clearly says that we are a buffer, and so this is Ka times Kb is equal to 1 times 10 to the negative 14th. And so Ka then times 4.4 times 10 to the negative 4th is going to be equal to 1 times 10 to the negative 14th. And so 1 times 10 to the negative 14th divided by 4.4 times 10 to the negative 4th gets you a Ka value of 227 times 10 to the negative 11th. And now that I have moved things back over to the acid realm, then I can go and use my Henderson-Hasselhoff equation, which is pH is equal to pKa plus the log of the ratio of the base to the acid. And so your pH is going to be equal to the negative log of 227 times 10 to the negative 11th. And then you're going to add to that the log of the ratio of the base to the acid, and so we just got to make sure that we know which one is the base and which one is the acid here. So this guy here, the methylamine, has the Kb, so that is the base aspect of things, so that's going to be 1.5 molar. And then we have methylammonium chloride over here, and methylammonium chloride has that extra hydrogen to it, and so that must be our conjugate acid. And so that is going to be a 2.5 molarity that's there. So consequently, we're going to logify this. And so my pH is going to be a 10.64 here. And then I'm going to do 1.5 divided by 2.5 and logify that. And I'm going to add to that a negative 0.22. So plus 1064 gets me an overall pH here of about a 1042.